Well, for feed-forward control, also I recommend to watch this video. It's explaining well the feed-forward control, basically what we said, but in addition, something new, we'll see it now.
So rather than invert the dynamics exactly, we usually try to fit a causal and realizable model to the inverse.
So yeah, here basically talking about the feed-forward controller design. It's G minus 1 of S, but sometimes we know this is not inversible, not realizable. So then we basically fit a causal, something realizable, and realizable model and causal model. So it's physical existing model, because we often we don't have an exact model of the system. So then we cannot accurately eliminate the steady state error if you wish, or the dynamic. We don't cancel the dynamic exactly. Okay, so and we know here it's demonstrated, of course we can follow it. So for a perfect model we have the feed forward controller design should be the inverse of the plant in this case, right? The inverse of the plant.
Dynamics as best as we can. So with both of these modeling limitations, it's impossible to completely remove the set point change error, but usually we can reduce it a lot. In this way, the feed-forward controller takes care of the bulk behavior, and the feedback controller corrects for the modeling errors.
So the feedback controller correct for the modeling error, and the bulk behavior and general behavior take care of it, the feed forward controller. Okay.
The goal is that these modeling errors can be corrected by a low bandwidth feedback controller, one that will still ignore the higher frequency noise.
So you can keep going over it if you wish. I'll go to here and show you now in the presence of disturbance.
Also need to find a way to measure the.
Yeah, so now in the presence of disturbance, remember this superposition theorem, so y is equal to u times the transfer function gp plus disturbance times the transfer function gd. Alright, according to the disturbance theorem, and we know how to find gp and gd. You have to input disturbance and control input, so these are my two input on the plan. U is the output of the controller, will u and d, these are my two input, and I have one output y. So y is related to u and d by this, according to the superposition theorem for a linear system, and which we know how to find it. In order to find gp, you cancel d. In order to find gd, you cancel u. You cancel this input and you keep the other input, and you find the transfer function. Well, if that's your transfer function, then what should be my feed forward controller in that case, in case of disturbance? Okay, so one time is to cancel the dynamics of the set point and canceling the steady state error. So then I know it is the inverse of the plant. That's my feed forward controller design. But what if I'm interested on the disturbance? So then should be the inverse. Is it simply the inverse of the disturbance dynamic, or also related to the plant as well? Actually, it's related to the plant and the disturbance dynamic. And my controller design, feed forward controller design, should be minus gd of s over gp of s. Of course, again and again, the disturbance transfer function model is not accurate. We don't know this perfectly, both of them. And the plant transfer function with the model of the plant, we don't know perfectly. But basically, so if we want u over d, it is minus gd over gp. So you can look at it. Basically we need y equals 0 to have perfect disturbance rejection. So then in the presence of disturbance, y should not be affected. This is 0. So then u over d, you get minus gd over gp. Okay, so then this will be your controller design, feed-forward controller design, in the presence of disturbance. As example, we here, so I recommend you to continue the video. Here you can go to this example, temperature control in heat exchanger. Well, this is a good example in math work. You can follow it. Basically, here you have a tank, water tank, and you want to control the heat or the temperature inside the tank. Given that you have liquid inflow, which is cold liquid coming in, and here you have steam valve that you can regulate the steam, the input steam, in order to keep the temperature constant, for example, at a desired value. So each time you have a disturbance is the liquid inflow, so then you may need to open the valve more to have more steam flow to the heat exchanger, and therefore keep your desired temperature. So if you follow step by step this tutorial, basically here they did the model by system identification. So they did some measurement, measured response to step change in steam valve voltage. So they did a step here, and they look to the tank temperature, where here they normalize it. They, for a step voltage input, they look to the tank temperature, and they measure those value, and based on this value they try to identify the system and having the transfer function. We can note that it's a transfer function with delay, but it's a first order system with delay. So how to find it? You need tau and d, and DC gain. DC gain is almost 1, right? It's 1, and tau they computed 21, and you have the theta, which is, if you wish, the delay 14.7. Well, this is somehow what you can do. You can do reverse engineering. If you have the transfer function, just make sure it is the same as the one you predicted, similar to your experiment, how close to it. We know that tau is 63%. Here they did it slightly different, but you could use, as we know, how to identify a first order system. Tau is 63, so you take T2 as tau if it is 63, and the delay is here at this point, and then e minus exponential minus that value over 1 plus tau s, and you check if it is the same. Well, in their method they take tau as 3 over 2 times T2 minus T1, where D2 is 63.2% and T1 is 28.3, and it seems to verify well their expectation. So you could use what we know about system identification of first order system and see how close it is from this one. Well, basically we get experimentally how the temperature change with time for a step input in the steam valve. So the voltage at the valve, I apply the step voltage at the valve, and I get measure the temperature, so I identify my system. In the same way you can identify the disturbance, like by applying a step disturbance. Here you measure also the temperature, how it's changed, without taking into consideration this, just one input output, so you can get the disturbance model as well. Well, here they get the disturbance model, it reflected by this delay and this first order transfer function, and here the heat exchanger model by this first order with delay transfer function. So this is basically my system. Okay, so the first one models how change in the voltage driving the steam valve opening affects the tank temperature. The voltage, which voltage driving the steam valve opening? Okay, this voltage here, how change the temperature. And the second model the second transfer function, while this transfer function models what? How a change D in inflow temperature affects T. Okay, and here they did a comparison between feedback and feed-forward controller. Don't forget, when you do feed-forward design, you need to take as a controller design minus GD over GP. If in this case we assume we know them perfectly, we know GD and GP, but in reality we don't know exactly remember GD and GP. We cannot have an accurate model, so and therefore we still have errors. Okay, so I recommend you to follow the tutorial. PI controller, we know how to design a PI controller. You can do automatic tuning if you wish, and find the controller that satisfy your requirement, your set point, and look to the disturbance rejection in this scenario, look to the time delay and so on, and later on add, because the disturbance is known, and I told you when the disturbance is known, so to have a faster response, then it's an advantage to add feed-forward controller in addition to the feedback controller. Okay, here they did first a comparison with in case of feed-forward controller only. Well, here they demonstrated to you like perfect disturbance rejection F equal minus GD over GP. You know GD, that's GD, and you know GP, then overall you get this transfer function. So then this will be F. Alright. So here they design only feed-forward controller in this case, not with feedback. And they try to simulate the disturbance rejection. Usually you have perfect disturbance rejection if you have the same delay, but here they change the delay a little bit. Like instead of minus 20 they use minus 25 because they assume we have error in modeling, just to show you how the disturbance will be rejected. Yes, here is they combine both together, feed forward and feedback, so the response basically should be faster than in the case of only feedback. Okay, that's the feed forward controller. It's added to the output of the controller effort because the disturbance is known again. So when the disturbance is known, again I recommend you to do it this way. Alright, or it could be measured. In case it could be measured, for example, the disturbance could be measured, so you can do it this way. Alright, and this is the response. So here you can see the disturbance rejection. Well, the set point tracking is the same for feedback only or feed forward plus feedback in this case. So the tracking is the same, but as in disturbance rejection performance, see how the disturbance rejection is better in case of feed forward plus feedback. Okay, so that's a disturbance step change. If I have disturbance step change, disturbance rejection is faster in the case of feed forward plus feedback, because we know we compensate for something we know, which is the disturbance. So that's the advantage of feed forward. So then make your system settle faster in this case. Here they show it to you in body diagram. You see how the disturbance, which is low frequency, for example, it's better, it has better rejection. Okay, so better rejection of disturbance. But for the settling point, for the set point is same. Good. You can interactively play with it in here in MATLAB if you wish. Alright. So here is the system. Here they consider zero set point. They assume the desired temperature is zero. So they are regulating, they are controlling to reach zero set point. You can change it by something else if you wish, but I'll keep it this way. Just your feed forward controller, we saw it in a while here. That's the feed forward plant. So minus GD over GP, and here is GD, here is GP, temperature. Okay, so basically that's the system we have. Interactively we can play with. And here, well, what do I have here? I have feed forward gain and feed forward delay, so which I can tune, I can change. Let's understand what else. Here is my open loop. That's how it looks like. This is the feedback control. That's the feedback control. And here is the feed forward controller as we know it. And here is both together, feed forward plus feedback. And we will see interactively here the disturbance, the temperature, and the voltage applied. Okay, so this is the voltage here. Okay, and the set point, again we saw the set point is 0, right? Don't forget the voltage applied is here. So I'm looking to V, which is voltage applied. Basically it's your control effort. Temperature is your temperature you are controlling. Is it following the 0 set point or not? That's what you care about. And the disturbance is what kind of disturbance you are applying. Well, as the set point is constant, I'm setting to 0. Also the set point at time equal 20 seconds, I'm going with a disturbance of -1, step disturbance of -1. Alright, and this is my feed forward control, which is I calculated in here, minus GD over GP minus 21.3S plus 1 over 25S plus 1. So minus 21.3 over 21.3S plus 1 over 25S plus 1. Alright, so it's the same. And this is the delay minus 20.3. I told you, take it a little bit different, so to have some to make it somewhere reflect the real situation, because you have error in modeling. But if you want to take it 20.3, feel free to take it. So here's the delay, here's the delay, they take it 25, you can change it by 20.3 as in your calculation. And this is again just it's 1, means nothing, but you can also change it to reflect more realistic scenario. Like you can change the delay, but also you can change again here to reflect more realistic scenario. So now if I change the parameter of my f, how this will affect my controller, because this f we know it's not accurate. So what if I change these two values, the gain and delay, and how this will affect my controller? Okay, here in the interactive things they are asking you, you may change the gain or the delay and see how this will affect the controllers. Now in the ideal scenario it's 20.3. Alright, that's the ideal scenario. So of course if it's open loop, I have GD and I have GP and GD. If I go here, if I'm open loop, just I'm going from here, GD, you have disturbance delay of 35, and so this doesn't affect the system. Now it's open loop, so whatever you change here, this doesn't affect the system. Basically those will affect the feed forward control, the F that you calculated, even doesn't affect the feedback, because the feedback is something you calculated. I took the controller which we get it from here, the feedback, the PI controller basically that we calculated so in this tutorial. So here the switch here is reflected by the fact that you can select from here, do I need feedback or I don't? If I have, so then it is not 0, if I don't have. So you know, this is this thing change here when you do interactively. Yeah, that's it. Remember, disturbance is at 20 seconds. Set point is my desired controller goal is 0. So of course, if I'm in a scenario of open loop, whatever I change here, this doesn't affect the system. Let's look to at 20 second. So you see I have disturbance at 20 second. And because I have delay, after some time, I start seeing the temperature drop, right? And it follow my disturbance. I have no control at all. Nothing applied. So my control effort is 0. Okay, that's the voltage applied. Uh, Look at it here. Set point is 0. You have no controller. So 0 controller. Then here is 0. Alright. So then it is like that. Whatever you change here, it doesn't affect. So this is open loop, of course. What if I'm using feedback? So now I'm using feedback. Look at, I have the perfect, well, but this is doesn't matter. Let's do feed forward if you wish. So I'm doing feed forward now, and I'm using exactly the same model. So look what do I will have. So at 20 seconds I have disturbance, I have delay. Then look to my temperature. My temperature is following exactly the set point, which is 0, with no error at all. But this is in reality it's not the case, because we know that we cannot have exact model. So let me have 25. Just also I can change the feed forward gain, so to make more uncertainty in my model, in my modeling of the, or in my design of the feed forward controller. But look at it how it is. This is the control effort V. V is the control effort that you apply to follow your step point, which is 0. That's the effort I apply. So now if I have 25, how it is robust to the model uncertainty? It's not really robust, because there is no feedback in this case. See the system how it behaves. Okay, so you can even make more uncertainty by changing the feed forward gain, but I don't want. So this is the how it looks like. What if I add my feed forward plus feedback controller both together? So how this will be affected? Okay, this is the control effort I'm using, and here I went back to my 0 set point after sometimes. Now I adding the controller, so which I already designed. Maybe you could design better than this controller. Okay, by doing automatic tuning or whatever. Here they didn't do automatic. They didn't do automatic tuning to compute the controller, but you can do yourself automatic tuning. No problem. Let's start this scenario. So I have feedback plus feed forward. So I can see now I have my system, my response is faster. Okay, so maybe you could have better even tuning of the feedback. What if you use the feedback alone? Of course, it's not as we are using both together. Okay? So you see that's the feedback alone. So it's not as good as if I have both together. Of course, if you have more uncertainty when you are using, when you compare feed forward, for example, with feed forward plus feedback with more uncertainty, you can see more in a more clear way the importance of feedback controller, because it will take care of modeling error. Okay. So now we learned how to design a feed-forward controller in the presence of feedback controller. Or also feedback controller, we know how to design it. we design it separately, then we design the feed forward controller if we have based on a model that we have. Um, that's basically how we design it. But what about not the feed forward controller, the feedback compensation, which basically I mean by that the controller which is in the feedback loop here. So how to design this controller? Up to now we didn't know, we didn't see an example or few examples on how we design this controller. Okay, so we was working some examples on how we work with this 2 degree of freedom controller, the feed forward controller, okay, in addition to a feedback controller here, classical way. But if the controller is in the feedback in here, in addition to a controller here, how to design the controller in this case? What's the strategy we will use? Well, that's what we'll see in the next session. But just I want to point out that this is actually is a part of something we call it multi-loop control. So here it is, because this is the outer loop and here is the inner loop. Okay, so this is the inner loop and here is the outer loop. So this is part of multiple loop control. So next session we will see multiple loop control and how we design a controller if we have multiple loop. Like take this example, I have a controller here and a controller here. So this is a multiple loop. So you have inner loop. This is the plant for the inner loop. So it's torque current control. So here is a current control and here is the speed control. So here I have a controller to control the current, the inner loop, and the outer loop I have a controller to control the speed. Okay, so if my two controllers are in this way, so how to design, how to find the controller? Or if it is in this way, but this is part of, in this way, this is part of also. This is the inner controller and this is the outer controller. How to find, how to design a controller in this case if I'm in this scenario. This is what we call multiple loop if you wish. We know this, we call it feedback compensation now, or velocity feedback in case you have derivative, but in the general term this is multiple loop. So here it's a scenario where I have multiple loop. It could possible to have not only two loop, inner and outer, maybe you could have a three loop even. Okay, so what are the steps and how we design for this scenario? We'll see, like next time we'll see examples on MATLAB, like if I have velocity feedback, the example we saw in the lecture, or in the example we know, or we have other example. We'll see other example like here, if inner loop and outer loop scenario, or again if I'm in this scenario or this scenario. We will see few example, inner loop, outer loop, next time.